Good day, people. In this tutorial, I want to say a few words about the measure inertia data icon that appears in the 3D Experiences uh, CAD workhorse, which is actually the CATIA program. Now, uh, in that dialog box, there are several tabs, and we're going to discuss that in a few minutes. And the strictly CATIA V5 version of this tutorial can be found in a playlist in my channel called CAD Aspects of CATIA V5. Okay. Uh, when you click on the Tools tab in the ribbon in the part design, for example, and you scroll to the right, you'll see that there is this icon which is called Measure Inertia tab. Okay. And you can see that it's very similar actually to what appears in CATIA V5, although the name has slightly changed and the icon looks different. And when you click on the um, on that measure inertia tab on this, when you click on that measure inertia tab, you get a dialog box, and in that dialog box that you'll see shortly, uh, there is a place where there are several tabs: main result, inertia slash G, inertia slash O, inertia slash P, inertia slash A, and inertia again slash A. Okay, so these are the tabs that I would like to discuss in the present tutorial in the context of 3D experience, or really it's CATIA 3D experience. And in the other video tutorial, just CATIA V5 version. So when you get the main dialog box, measure inertia tab, it is possible to customize so that not everything appears. So if you want everything appears, such as these tabs that I mentioned, you click on the customization and check all of these, and that's what I've done. Okay. Now, when you do that, the dialog box looks like that. Okay. So here are the tabs that I mentioned. The main result basically gives you information about the area, volume, mass, etc. And then we're going to look at the other ones in a minute. Okay. By the way, notice that you have option of selecting a volume or selecting a surface. Okay, so some of these may not be applicable to surfaces. So here's a three-dimensional object generated somehow, either in 3D Experience or some other CAD package. So you ask the question uh, yourself is if assuming that the density is given and is constant, what is the moment of inertia of this three-dimensional object? Well, can't answer that. Okay, we need more information. You have to tell me, you have to give me more information. You have to, first of all, give me an axis system, because you cannot talk about what is the moment of inertia number-wise unless you have an axis system and a place where you put that axis system as its origin. Okay, so basically, you give me an axis system, you give me a point, and transfer that axis system parallel. So these are parallel. X, Y, Z axis system is parallel to whatever was given to you, and the origin of it is at the point P. Now we can actually say, we can actually calculate the well, the inertial tensor. Okay. Now inertial tensor, that's a loaded word. Inertial tensor is a 3 by 3 matrix. The stuff on the diagonal are called moment of inertia, and the stuff that are off diagonal are called products of inertia. Just keep that in mind. So, for example, once I have my coordinate system set up and the point P is given to you like that, then I can talk about what is the X value, what is the Y value of every point associated with this coordinate system. Then it makes sense, okay? So these things are called moments of inertia. These appear on the diagonal, and these are called products of inertia, which are off diagonal. Now, notice that in some textbooks, they put a minus sign here. Just be aware of the fact that in CATIA, that's how uh, uh, the inertia product of inertia are defined. Okay. So uh, once you define a density on that part, that obviously you need the mass. Notice here, these are dm. That means you have to know the mass of things that you have to know the density of things. So first of all, main result, I already told you that it just gives you, area, volume, mass, etc. If you click on inertia slash G, it will give you 6 numbers here. These 6 numbers, the ones on the top, the ones are the diagonal term, in other words, Ixx, Iyy, Izz, and these are called moment of inertia with respect to a point which is the centroid of that part. In other words, we are already saying what the point where we calculate things are with respect to, that is the centroid. That slash G means that the point given is the centroid of the part. And since there was nothing done about the axis system, it's the global axis system that we're talking about, part axis system, main axis system. So what it means is that you go to the centroid, you draw an axis system which is parallel to the part axis system, the main part axis system, and then you can calculate these things, and that's what these are. Okay? All right. When you click on with respect to O, this O, that means that the point that you fixed and you put the axis system at it is not the centroid, but it is the the origin of the part. Okay, so wherever you created your part, there was an axis system XYZ, and there was an origin O. So it is going to use that point as the point where the coordinate system is drawn from and is calculated like that. For example, hypothetically, if the point O and the point G were the same point, in other words, you created your part so that the part centroid was actually at the global origin, then you'll get the same numbers in general. Now, with the slash P means that point you select the point P, whatever you want, not G, necessarily G, not necessarily O, any point out there for convenience, you can select it, and then it's going to put the coordinate system, the global coordinate system, because you haven't done anything about the axis system. It's always referring, right now, it's always referring to the global axis system XYZ. It puts it at the point P, and then it can calculate the stuff. Okay, those integrals basically. Now, inertia slash A. Notice that these both kind of say the same thing, but they are different. See that this is with respect to an axis, this is with respect to axis system. So what this thing means is that you select a line or a direction, let's put it that way, a direction, and starting at a point, so there's a point, you have a direction, okay? It could be that the point was not explicitly defined, but it's the end of the line, for example. And it's going to calculate the moment of inertia with respect to that direction, with respect to axis. I will do an example in a few minutes. And then it also spits out the moment of inertia and the radius of what is called radius of gyration. We'll get to that later. And finally, this last tab is you select an axis system. Okay, you select an axis system with whatever the last point of reference was. In other words, if you were doing things with respect to G to begin with, and you select an axis system, it's going to take that axis system, draw it from G, and start doing the calculation. Okay, if you are just actually, I have to correct myself. So when you select an axis system, the point O is going to be the origin, that the origin of the axis system is going to be listed here. Okay? So if the axis system just happened to be at the centroid, then of course the point O will be the centroid. We'll move on. Now there are some references, not very informative, about some of the things that we're talking about. Now, I'm going to do that in the context of an example. So two examples actually. One of them is like this. We have a 3 by 2 by 1 box, okay? 3 by 2 by 1 box, which has a density, say, density of 1 kilogram per meter cube for convenience. I mean, this is nothing. Steel is about 7,000 kilogram per meter cube, but they're going to assume that it's 1 kilogram per meter cube. That really doesn't do anything as far as numbers are concerned. It just magnifies that. Now, if you wanted to find the mass moment of inertia of this box with respect to the centroid, these and directions x, y, z that are given, principal direction, then these are the formulas. And if you wanted some other axis using parallel axis theorem, some version of parallel axis theorem for a moment of inertia and product of inertia, you can use it. But it's a lot of work. I mean, even for a cube, it's going to be a lot of work. Now, the example that I'm going to do at the end is take a box of dimension 1 by 1 by 1 and a density, for example, 1,000 kilogram per meter cube. I don't know why I changed it to, instead of 1, I changed it to that. And then, oh yeah, I know why, because anyway, so what we want to know is the moment of inertia of this box with respect to that line, and we're going to check that, okay? And if you look at it based on direct calculation, okay, you should be getting 0.408. This is hand calculation, okay? Because there is a formula for this. This is coming from Miriam's book. The analytical solution is this. And to find the radius of gyration, you need to know the mass of it. Anyway, you use the mass. Let's go ahead and do that. So we're going to go to 3D experience. I'll make a box, and when I make it, I make sure one corner of the box is at the global origin. So on that horizontal plane, I will sketch. I've already changed my units so that they're all meters in kilogram. So the box is drawn like this, starting here. Notice that this is the direction Y, this is the direction X, okay? So I'm going to dimension some of these things. This is going to be 2 meter. Okay. And this is going to be 1 meter. Sorry, this should have been 2 meters. The other one should have been 3 meters. That should have been 3. Okay, so exit. So what we have here is 3 meters in the Y direction, 2 meters in the X direction, and let's pad this thing up by 1 meter. So notice that that corner at the left back there is the global origin. In fact, for me, because you can see that in intersection of these 3 planes too, but for me to see it better, I'm going to click on the axis system. It's going to put it there. So this is the global origin. The part origin is right there. Very good. Okay, now, so let's go ahead and see what's going on. Oh, we want to apply material to this. So I'm going to go and to tools. And there is a material. I'll make a material. Create a material. I'll call it checking tabs tutorial. and then we say okay. It's going to create that, and when you apply, we apply to that part. Apply to this part. Good. We don't need that anymore. Oops, did I do that? Let's try it again. Apply to this part. Green check marks. Oh, it's already there. Yeah, good, good. Close this. Okay, if you double click on this line, it tells you that the density of the material is 0. So we agreed to make that thing 1, right? So when we do that, of course, the mass of this thing becomes 6 kilograms. So apply. Good, and close. All right. We don't have to specify the other properties. All we need is the density that's applied this way. Now, so we click on the tools, you scroll to the right, and we have measure inertia. Measure inertia. Okay. So we select the volume. Okay. And notice what happened here. First of all, in the customization, if you look at it, everything is selected. That's why I've got all the tabs here. And this is the main result. It says the volume is 6 meter cube, 3 by 2 by 1. The mass is 6 kilogram because the density was 1 kilogram per meter cube. And the center of gravity is that location, which is 1 in the x, 1 in the x, 1.5 in the y, and z. So everything looks good. Now, if I click on the inertia, see that? Inertia with respect to g, it will give me the inertia matrix or inertia tensor or 6 numbers with respect to the original coordinate system, global x, y, z, in the directions that were shown, and at the centroid. Centroid is right there. And here are the three diagonal terms. These are mass moment of inertia. And here are the 3 products of inertia. But because this is symmetric with respect to the origin, with respect to that coordinate system, these are all 0. Notice that there is a result which says that if, for example, hypothetically, if x, y is your plane of symmetry of the object, anything that has z in it in the product of inertia is 0. Anyway, so the product of inertia is 0. All right. Now, if you click on the inertia slash O as the reference point, it does not use the central mass, but it will use the origin of the global coordinate system, which is right there. So if I click on that, because the x, y, x, z, and y, z planes are no longer planes of symmetry, you have products of inertia, okay? Everything will change. So moment of inertia will change, and product of inertias will change. It was 0 before because g was the mass at the symmetry location, but now if I use the global origin slash O, global origin, original coordinate system, there will be negative numbers here. Now, if I click on, for example, inertia, and I select that same point, obviously, you're going to get the same numbers, okay? Because if I select as my point is that corner, nothing is going to change because that corner was already uh, checked. Okay, so what I can do is I can go, for example, select a different corner, maybe this corner, or I can create a point and select that point. Now, I don't want to create a point, but if you select that, it means that this is take the XYZ, put it at that location, and use it to calculate these things. So if I select this, oh, you have to check this box, select the point, have to do that, and select this location. I don't know how to do that. There. It tells you what point you picked and what are the resulting mass moment of inertia and the product of inertia with respect to this location having the coordinate system aligned with the original coordinate system. Now, let me cancel that for a second. So I want to do something here. So uh, suppose I go and create a coordinate system here which is not aligned with that. Now, how do I do this? We can go to the part, essential. Where's the axis system here? Just a second. Essential. There's the axis system right here. Suppose I create an axis system just like, let me see, just like that. Z this way, X going down. Okay, let's try it. So origin is that location, X going down, Z going, I can't remember, forgot. Z going, okay, Z going this way, select this, Z going that way, and also reverse it. And for X, even for X, you reverse it. Okay, now it's good. Z going to the right, X going down, and Y going away in the direction shown. Okay, so let's go back here. Say okay. All right. Now, by the way, when you do that, when you create a coordinate system, axis system, it uses it as a current. If you don't want it, just make it, uncheck it, just uncheck it, make it not as current. It really doesn't matter for us. With that set not as current. That's fine. Now, we go to tools. Let's go find that inertia thing. Measure inertia data. See that? Measure inertia data. Okay. And we have already customized. Everything is showing. Select the volume. There's the volume. Now, if you go to the last tab here, inertia slash A, see that? It says select your axis system. In other words, don't use the global axis system. Select the axis system, this axis system. Okay, select the volume, go to the very last tab, inertia slash A, inertia slash A, select the axis system, and select it from the tree, for example, the second one. Okay, and notice that we now have this point as the origin. The axis system is sitting there, and these are the numbers. Okay, and this is going to be different. The numbers are going to be different from what I have already done because I already selected the point here. You remember that? But there, the axis system was XYZ, original global axis XYZ. Not anymore. This is not the global XYZ. It's the XYZ that was created like that. Now, the only one that I have not done incidentally is I've not told you anything about this fellow. Okay, so let me do the following. Cancel that. I'm going to start another part because I want to do it in the context of uh, this example, this one. Okay, so let's go out here. Let me start another part. I can use this one too, but I'd rather not. Okay, so uh, what I'm going to do is the following. I'm going to on that horizontal plane, I will sketch a one by one. I'm going to draw a rectangle, but on purpose. This is now on purpose. I'm going to draw it like this, a rectangle like that, dimension it, 1 meter here. Oh, Control Z, 1 meter, 1 meter, okay. And same thing down here, 1 meter, good. And exit. I did it on purpose. On purpose, I didn't want to draw it very uh, aligned with the axis system here. So let's go and pad it. How about making it 1? Good. So there it is. Now, I'm going to draw a line from there to there because this is going to be the direction where I want to calculate my mass moment of inertia with respect to. So point to point. So a line from this point to that point. Very good. Let's apply material to this thing. So under tools, I already have the well. Let me see now. What do I want to use? What do I want to apply as density? 1,000. Okay, 1,000. So I'm going to create a new material. Uh, second material. Second example. All right. Say OK. And then we're going to do apply to that part. Okay. There we are. We don't need this anymore. I don't need that anymore. Double click on this and put 1,000 kilogram per meter cube. Okay. Apply and close. Okay. So we go to tools. We go to measure inertia. Select the volume and inertia slash A here, the second one from the right that I've not done before. And I'm going to select that line, that direction. See this? Let me see if I can pick it from. Oh, select axis. I keep forgetting checking this box. And now we can select that line. I keep forgetting checking this box. Without that, you can't do it. You can do it from screen 2 or from the tree, but without checking this, you can pick it. Okay, good. And look at what happened. It tells you what is the direction of this line. Where is the origin of it? The origin of it is, I don't know, it's either this point or that point. It really doesn't matter. Here is the mass of it. The mass moment of inertia, not the mass of it. Mass moment of inertia is 166.7. And if you check at it, that's exactly what comes out of the Merriam's book. And the radius of gyration is square root of I over m. I over m. We have m, we have I, and if you calculate theoretically, it's 0.408, and 3D experience also give you 0.408. So that's what these tabs are for.